Okay, so that's the last video for the day. I cut off at 0.973 for R because I wanted to talk about what does it mean. We had an n equals 6 and 0.973 for R. I of course said R would be between -1 and 1. 0.973 is really close to 1, so that really means we have a positive correlation. Now, that process, even with just doing 6 things, is long. Now, your calculator can do it. There's an explanation at the bottom of page 7 on how to do it in your calculator. If you were struggling to use the calculator, since this class is online now, if you just Google linear coefficient calculator, you can find any number of online tools which will calculate it for you. Now, to say a correlation is strong, we must have an R bigger than the value for the given n. The table for that is on page 8. So our n was 6. So what's the critical value for n equals 6? It's 0.811. Is our R bigger than that? Yes, which means we have a strong positive correlation. Now, it says to do the same thing for the absences. This is the table from page 4. So what I'm going to do is I'm going to put what the table is on page 4, and I'm just going to use an internet calculator to calculate what this R is. So we calculate the R for the absences, and here's the table that we use. And from my calculator, it looks like R is negative 0.8998, which would round to 0.900. Now when it's negative, instead of being bigger, you have to be smaller. So it's like the absolute value is bigger. Now there's 7 entries. So for n equals 7 on the table, my critical value needs to be 0.754. So we take the absolute value of this thing is 0.900 greater than 0.754. Yes. Now, because this is negative, we say it has a strong negative correlation. So just remember that if it's negative, that you're really taking the absolute value and comparing it to that critical value. Now, one thing to note, correlation doesn't mean causation. You're like, what does that even mean? Just because two things are related doesn't mean one causes the other. For example, on page 9, it shows a table with a negative correlation, which means ice cream and flu cases are negatively correlated based on our graph. What does that mean? Well, if you assume that correlation means causation, you assume that increased ice cream sales cause fewer flu cases. I'm pretty sure ice cream is not the cure for the flu. So what we usually can have is called a lurking variable. So so if you assume correlation means causation, you say ice cream cures the flu because more ice cream sales had fewer flu cases. Probably not. So the lurking variable is a hidden thing related to both x and y that can explain why these are related that way. So what would a hidden variable be? Well, sick people tend to not go out and buy ice cream or buy anything at all, so sick people stay home. So if there are more flu cases, then there are less people out buying ice cream. If there are less flu cases, there's more people out, so therefore there are going to be more people out naturally buying ice cream. So that's just one thing to note. This is all of the 4.1 notes, and we'll do 4.2 on Monday, and that is our last thing.